This Exambite video will look at the exemplar listed on the NZQA website for Physics 1.1 Assessment Task Spring Experiment. We'll look at the grade boundary for high merit, low excellence, and we'll correct the mistakes made by that student. This assessment activity required you to find the mathematical relationship between the stretched length of a spring and the mass that is hung on one end to cause it to stretch. Shown in a diagram, we've got a spring on the left-hand side without any force being applied to it. Then on the right-hand side of this diagram, you can see that when we hang a mass at the bottom of the spring extends and we measure that stretched length. Now the mass needs to be expressed as a weight force in this investigation. And we calculate that weight force using the equation weight equals mass times gravity, or W equals m times g. For example, if the mass was 50 grams, then the weight force would equal 0.05 kilograms times the force of gravity, which is 10 newtons per kilogram, which equals 0.5 newtons. So what mistakes did the student make? Well, the first mistake relates to that point we just made previously. The calculation of the force values was not carried out correctly, as the mass values used were in grams rather than kilograms. So for example, what the student did wrong, let's say that the mass was 50 grams, then the student calculated it using the correct equation, but used the mass in grams rather than kilograms. So for example, weight equals 50 grams times 10 newtons per kilogram, which gives an answer of 500 newtons. Now we need to make sure that the units are consistent throughout the calculation. So if we've got newtons per kilogram for the force of gravity, then the mass needs to be in kilograms for the calculation to work correctly. Now 500 newtons, this answer is equivalent to the weight of an average woman, for example, 50 kilograms of mass. So that's a lot heavier than the 50 gram mass that the student would have used in the investigation. So this is wrong. To do it right, we need to take that 50 gram mass and we need to convert that 50 grams to kilograms by dividing it by 1,000. And then our calculation changes. It becomes weight equals 0.05 kilograms times 10 newtons per kilogram, the force of gravity, which equals a modest 0.5 newtons. And that's correct. The second mistake that the student made, when the lengths were averaged, the extension lengths, a number of the averages were calculated incorrectly. Now, before we go into this, it's important to identify first that the student didn't actually measure the full length of the spring. They just measured the extension length, the length that it extended by. Okay. Ideally, you would actually measure the whole length of the spring, although it still gives a similar result. Okay, so looking back at these averages, the values for three trials for one of the masses that the student used were 0.035 meters as the extension length, 0.037 meters, and 0.040 meters. Three very closely grouped values, so we can determine that they are probably quite accurate and close to the true value for that mass. Now we need to calculate an average. That improves the reliability of the experimental data. Now the student calculated the average as 0.025 of a meter from those three values, and we can look at that and say, well, that's clearly not right, because for those three numbers, if you've done a few calculations of averages in maths, that just doesn't sit anywhere within those three numbers. So that's clearly incorrect. And you should be able to identify that either by double checking your calculation or just, identifying it because you've done so many average calculations before. So if we do that correctly, what we find is that if we use the same values for the three trials that the student used, if we do the average calculation correctly by adding those three numbers together and then dividing that total by 3, because there are three numbers, then the average works out at 0.037 meters. That's to 3 decimal places, which is much more accurate, and obviously it sits within those 3 numbers, so it's believable, it's plausible. Right, moving on to the third mistake. 2 of the points were plotted incorrectly, but 8 were correctly plotted on the graph that the student drew. But it was these 2 points that caused the students, again, the marker to grade the student down from that excellence. Okay. So if we look at the chart, then there were 2 points that were incorrectly plotted on the student's chart. Now this chart that you're looking at here is one that I did using Microsoft Excel, which plots very, very accurate graphs, and it's using the same values that the student collected, and we can see that those points there, if they're correctly plotted, that's where they sit. The student, he might have looked at them and said, hey look, they're not sitting that close to the line, so what I'll do is I'll just plot them a little closer to the line and make it look like they sit closer to that line of best fit. However, the marker has identified this incorrect plotting and graded the student down for that. In this situation, the best thing to do is to plot the points correctly from your data, assuming that you've calculated your averages correctly, plot them correctly, and then identify whether or not any of those points are what we would call outliers, which sit well outside of the line of best fit that we have identified, this linear straight line relationship. And you can clearly see there is one that seems to sit well outside the line of best fit there. And we call this an outlier, and we would ignore it when drawing that line of best fit in, because we would identify it as far out from the rest. Probably a mistake's been made somewhere in gathering that data. Mistake 4. When determining the run in the gradient calculation, the force scale was read incorrectly, and so the value of the gradient was not calculated correctly. So the student actually read data off of the graph incorrectly, and so got an incorrect value for his or her gradient calculation. Okay, so this is what the student did. If you look at the exemplar, the student calculated gradient correctly as rise over run. Gradient is given the letter M. The student used these values for rise, 0.170 minus 0.016, divided by the run, which the student used values of 4100 minus 494. Now, if you actually look closely at the student's graph, they've read this incorrectly off the graph, and so those numbers for run are not quite correct, which means these numbers are not quite correct. 0.154 divided by 3,610, that's not correct, and so the final calculation of 4.27 by 10 to the minus 5 is incorrect as well. Now, of course, the student made the mistake initially, mistake 1, of calculating the force incorrectly. So these force numbers are all incorrect, but the marker isn't bothered about that. They just want to see if they can read off the graph correctly and then calculate a gradient from those values. The fact that the force numbers are incorrect, it doesn't really matter. Right, so this is incorrect. So let's look back at that graph. Now, what I would do in this situation to get the rise and the run is I would look at a point along the x-axis, say 0.4. I would look up from that, and my rise, this red line here, would be calculated as the top y value there of 0.174, where the line is, minus 0, okay, because it's that whole length of that red line right down to the 0, and that equals 0.174. That's my rise. Now my run is from that point of 0.4 all the way back to the 0, which is of course calculated as 0.4. So that's a nice easy way to read the graph. When you look at the student's exemplar, it's not such an easy way to read the graph. Why not use this? It's a linear relationship, and so we can calculate it at that wide point along that line. So back to the correct calculation then, using those numbers. The rise is 0.174 minus 0 divided by the run of 0.4 minus 0. which works out to be a gradient of 0.44 when rounded off to 2 decimal places, which is very different to the gradient that the student calculated for a couple of reasons, but mainly because I used the correct force values there of correctly calculated force values. Remember to visit www.nztutor.co.nz for more useful resources.